Welcome to This Explainer. Today, we're taking a virtual journey to unpack the extreme physics and, honestly, the absolutely incredible engineering behind launching into orbit. And of course, the really tricky part, surviving the drop back down. Let's get right into it.
So, as we begin our ascent, I want you to keep one big question in the back of your mind. Where exactly does the sky end and space begin? You know, it sounds like a simple geography question, right? But the answer actually relies entirely on some pretty intense physical forces.
Here is our flight itinerary for today. 1. The edge of space. 2. Orbital versus suborbital flight. 3. The heat of re-entry. And 4. Designing the heat shield.
All right, starting off with Section 1. The edge of space, defining the boundary.
This brings us straight to the Kármán line, sitting right at 100 kilometers. That's about 62 miles above mean sea level. This is officially recognized by the FAI as the conventional edge of space. Basically, it's the formal jurisdictional boundary where aeronautics ends and astronautics begins. But why exactly 100 kilometers?
Well, Theodore von Kármán, the brilliant engineer this line is actually named after, realized something pretty profound. He saw that at this specific altitude, the atmosphere becomes so incredibly thin that an airplane would have to fly unimaginably fast just to generate any aerodynamic lift. Basically, at 100 kilometers, the air just gives up. Lift completely stops working, and centrifugal force, or inertia, has to take over the job. So it's not just a line on a map, it's a literal physical transition from aerodynamics to space physics.
Moving on to Section 2, orbital versus suborbital flight. How do we fly there?
So once we cross that boundary, the crucial difference between orbital and suborbital flight really comes down to one single thing: speed. A suborbital rocket basically just flies straight up, hits the edge of space for a few fun minutes of weightlessness, and then falls right back down. But orbital flight, that means traveling fast enough to achieve true orbital velocity. You're continuously falling around the Earth without ever actually hitting the ground. To really wrap our heads around orbital velocity, let's use a classic analogy. Imagine throwing a ball at ground level. Thrown at a normal speed, it travels in a little arc and hits the dirt. But if you were to somehow attach a rocket to that ball and shoot it forward incredibly fast, as the ball drops toward the ground, the Earth's surface would essentially curve away from it at the exact same rate. The ball is constantly falling, for sure, but because of its massive forward momentum, it just keeps missing the Earth entirely. And that, right there, is exactly what an orbit is.
Let's put some real numbers to this to see how crazy it gets. To reach an altitude of about 125 miles, think about the speeds we're talking about here. A normal commercial airplane cruises at around 575 miles per hour. Now, a suborbital rocket needs to hit a staggering 3,700 miles per hour. But to actually achieve a stable orbit at that exact same altitude, a spacecraft has to scream along at 17,400 miles per hour. I mean, that immense, mind-boggling speed is exactly what makes orbital spaceflight so technically complex and vastly more expensive compared to just popping up into space and falling back down.
Which brings us to Section 3, the heat of re-entry, surviving the descent. Now, if you're looking out the window of a returning spacecraft, your entire view would be consumed by a literal wall of fire. But here's a really fascinating misconception we need to clear up. It isn't actually friction causing all that heat. Nope. As the vehicle slams back into the atmosphere at hypersonic speeds, the air in front of it just can't get out of the way fast enough. So this results in a brutal, violent compression of gas and air particles right against the nose of the craft. And that enormous compression, it generates absolutely unfathomable heat. We're talking up to 7,000 degrees Fahrenheit. Just to survive that, the spacecraft has to withstand this total inferno, all while undergoing a massive, bone-rattling aerodynamic slowdown. It is easily, without a doubt, one of the most dangerous phases of all of spaceflight. And that leads us to Section 4, designing the heat shield, NASA's entry systems. Look, because human lives and billion-dollar payloads are on the line here, researchers at NASA's Ames Research Center absolutely do not guess. They test, and they test relentlessly. Using ground-based arc-jet facilities, they literally blast physical models with gas artificially heated to temperatures hotter than the surface of the sun. They then take all that physical data and combine it with rigorous, highly predictive supercomputer models to find and fix any tiny faults long before a real flight ever happens.
All of this intense testing has driven just an incredible evolution in thermal protection systems. NASA has developed materials like Pica, which is a foundational carbon ablator they've used since the 90s.
Then there's heat, the super cool 3D woven material built for extreme environments, like entering the Martian atmosphere, that manages to slash the mass by 40%. But honestly, the most mind-blowing one has to be Adept. This is an adaptable system that literally deploys in space like a giant heat-shielding umbrella made out of rigid carbon fabric. How wild is that?
So we've journeyed all the way from the loss of aerodynamic lift at the Kármán line up to those staggering 17,400 mile-per-hour orbital speeds, and then safely back down through a brutal 7,000-degree wall of compressed air. Now that you've got a solid grasp on the extreme physics involved in a journey to orbit and back, I want to leave you with this thought. As private companies continue pushing the boundaries of what's possible, how are these incredible entry systems going to shape the future of everyday commercial spaceflight? Will it ever become as routine as catching a flight across the country? Thank you so much for joining me on this explainer, and hey, keep looking up.